Let's talk about mass versus weight. So this is just a few slides into the notes. And we have already looked at mass as inertia. So now we're going to kind of go back to chemistry and think about mass being the amount of matter in an object. So basically that just means the atoms that make up all objects, okay? The stuff that makes up the object is what gives it its mass. There are a couple of common misconceptions. One is that mass and volume are the same, and they are definitely not. Volume is the space that the atoms take up, okay, and that changes on a pretty regular basis. We talked about in class how when you eat something super salty and you get really puffy, your volume has increased, but then by the next day you're back to normal, okay? Your mass does not change very much except for over very long periods of time, okay? The other common misconception is that mass and weight are the same, and they are not. We'll talk about weight in just a few minutes, but just know from the get-go that mass and weight are not the same. They cannot be used interchangeably, okay? We will measure mass in kilograms, not in grams, so that's an important part because kilograms is not the base unit, right? But it's considered the standard. 1 gram is about the mass of 1 M&M, so that's really, really small, which means that most objects would have a huge mass, right? So generally, high school students are between around 40 and 100 kilograms or so. So if we were using grams, that'd be 40,000 grams or 100,000 grams. That's a unwieldy number to work with. So we use kilograms as our standard. If ever you measure something in grams in class, you need to remember to always convert to kilograms before you calculate anything, okay? And then the last little bit to think about conceptually is just that because mass is the amount of atoms that make you up, that doesn't change if you go somewhere else. So if we take a class field trip to the moon, you still have all your atoms, you still have about the same mass, okay? The only way that would change is if you like lose an arm or something. So mass is relatively static, it's stable, it stays the same. We measure it in kilograms, and it is not the same thing as the volume. Okay, so now we're going to compare to weight. Weight and mass, again, are not the same. Weight is gravity's pull on your mass. Okay, so it's the force of gravity affecting the atoms in you. We actually have a formula for it. And so our formula is this one. Force of gravity is F of G. That's a little subscript G. Is equal to mass, which is the M, times the acceleration due to gravity, which is the G. On Earth, that's 9.8 meters per second squared. Weight is a scalar value. It does not have a direction associated, so you can drop the negative off the G for now. Remember, mass has to be in kilograms. And then we measure forces, all forces in newtons. Okay? So you can use weight and force of gravity interchangeably. That works. And because weight is a force, we're going to measure it in newtons and not pounds. So you can go ahead and just forget about pounds. We won't ever use it in our class. All right, so let's see what we know. Do our concept development here. First little block here says we want to use the words mass, weight, and volume to complete the table. So force due to gravity on an object. Well, the force caused by gravity is the weight, right? The quantity of matter in an object, or the atoms in the object, is going to be mass. And then the space that the atoms take up is going to be the volume. So again, those three are not the same, and it's important to make the distinction. Part 2, they show you that in letter A, the force exerted by gravity on 1 kilogram is equal to 9.8 newtons. So the way that they did that is they used the F of G formula, M times G. So they put 1 kilogram times 9.8 meters per second squared, and that gave us the 9.8 newtons. Okay, so letter B, we have 5 kilograms. We want to find the weight. We're going to do our 5 kilograms times 9.8 newtons, or 9.8 meters per second squared. And when we put that in our calculator, we find that that is 49 newtons. So an object with a mass of 5 kilograms weighs 49 newtons. Okay, we're going to skip C and D because we'll have some more practice down here. So again, the melon has a mass of 1 kilogram, so we would multiply to find the weight, and we get 9.8 newtons. So 1 kilogram times 9.8. And again, I'm using the formula Fg equals m times g. The apple has a weight of 1 newton, and we want to figure out how much mass it is. So if we write it out here, we see real quickly that we're going to have to divide to answer this one. Okay, so 1 divided by 9.8 is about 0.1 kilograms. Okay. Our physics book is 12.7 newtons in weight. So if we do 12.7 divided by 9.8, we get 1.295. So we're going to round that to 1.3 kilograms. So we'll make ourselves a little note that we divided to find that one. And then Uncle Harry is 90 kilograms of mass. So 90 times 9.8 gives us Uncle Harry's weight, and that is 882 newtons. So for that one, we multiplied. Okay, so a relatively simple formula. You're just either multiplying or dividing. Like always, just fill in your numbers and work the algebra, and you'll get it. Okay. And then the last part of this is there's a lab called Mass versus Weight, and there's a section at the end of it where we ask you to solve for your own mass and weight on the Earth and then on some other locations. So step 1 is to figure out how much mass you have. Okay, so that's actually just a conversion. You're gonna take your weight, and you can use your actual weight, or you can make something up. Let's say we go with 150 pounds. And we want to turn that into kilograms. Well, we want to get rid of pounds, and we want kilograms. And we see in our conversion here that 1 kilogram is equivalent to 2.205 pounds. We can check our units. They cancel. So mathematically, we're going to do 150 divided by 2.205. And we get approximately 68.03 kilograms. Okay, so again, we measure mass in kilograms. When you calculate yours, it should be smaller than what you think of as what the scale would tell you. Okay. Next step is we're going to calculate your weight on the Earth, and we measure weight in newtons, not in pounds. Okay. So to calculate that, we're going to do this formula here. We need to put in the mass that we just got, which was 68.03. And then G on Earth is 9.8. And so we get an answer of 667 newtons. And of course, I'm rounding that a little bit. Okay. Last step is to calculate your mass or your weight in 3 other locations. So in every case, you're still using the Fg equals m times g formula. The mass will always be what you calculated in step 1 because remember, the mass is the atoms that make you up, and that doesn't change based on location. Okay? The g will come from this chart over here. So people have calculated or measured the g, the acceleration due to gravity on these other planets, and so you can use that to solve for your weight. You'll see, like, if you go to maybe Pluto, you're doing your mass times 0.69, so you're not going to weigh much at all. Maybe you go to Saturn or Jupiter, your g value is much higher, and so you're going to weigh a lot more. Or maybe even you go to outer space, you weigh nothing because it's your kilograms times 0. And that explains why astronauts float in the space shuttles. Okay, so give the mass versus weight problems a try. Do the last bit of the lab if you haven't already. And as always, ask your teacher if you need help.